last time, if you have a subgroup of a finite group and the order of that subgroup specifies the order of the group, that was Lagrange's theorem. Also, the order of the element of the group provides the order of the group. And we also counted left cosets. Now, in this last little bit about group theory, before we move on past that, I want to tell you about what we call normal subgroups. Now, we defined a left coset. That is to say, H is a subgroup of G. Then the left coset it look like this. Because you multiply the single fixed value x on the left by everything in H. Right cosets I haven't talked about that until now, but now's the opportunity. Well, what a shocker. It looks like this. Now, let me point out that if the group is abelian, oh, somebody remind me what that means. Order doesn't matter, that's right. If G is abelian, then this distinction here, left coset, right, makes no difference, right? Because it doesn't matter which side I put X on if it's abelian, right? So, for example, let me do a coset where we add things, right? If G is Z and H is the even integers, then the coset, in this case, 1 plus 2Z, this is just a set of all odd numbers. Not 0. It doesn't matter whether I add 1 on the left or the right of an even number, I'm still going to get the same odd number. Same set. But it may make a difference if the group is not abelian. So here is an example to illustrate this. Let's go back to my old friend S3. Now I'm going to look at a couple of subgroups here in left and right cosets. In this case, pick me any element of S3. Okay, how about 1, 2, 3? Let's do this. Okay, let's look at this left coset. Basically, that just means I cruise through the elements of H and multiply on the left by 1, 2, 3. So I get 1, 2, 3, E, and 1, 2, 3, 1, 2. today, this comes out to be the set 1, 2, 3, this left coset, and what's the other one? 1 goes to 2, 3. So let's see, 1 goes to 3, 3 goes to 1, and 2 better go to itself. I'll check that. 2 goes to 1, back to 2. Okay, good. That's my left coset. Everybody okay with that? How about the other way? Let's multiply this on the right. Huh. 1, 2, 3 again, no problemo. What about the other one? Let's see, where does 1 go? It goes to 2 and then back to 1. Now let's see, where does 2 go? 2 goes to 3 and then it's left alone. And 3 goes to 1 back to 2. So I can erase that 1 if I like. Notice my left coset and my right coset are different. Do I agree with that? Now, they don't have to be. Let me give you another example. Let's take a different subgroup. This subgroup of S3 that consists of the identity in the 2, 3 cycles is also a subgroup. Now, let's look at what left cosets and right cosets look like. By the way, well, let me just start off with something. Okay, so let me compute this. 1, 2. This is 1 goes to 2 back to 1, so there's no 1. 2 goes to 3. 3 goes to 2. I guess I just did that over here, didn't I? And this one is 1 goes to 3. 3 goes to 2 back to 1, and 2 goes to 1 back to 2. Am I okay with that? That's what my left coset looks like. What about my right coset? This is 1, 2, but now I'll put the 1, 2 on the right. Let's do this. 1 goes to 2 to 3, and let's see, 3 goes to 1, and 2 better go to itself. 2 goes to 1 back to 2. Okay, good. And for this one, 1 goes to 2 back to 1. So 1 goes to itself, 2 goes to 3, and 3 goes to 2. Notice I got them in a different order, but I got the same set. Agreed? 1, 2, 2, 3, 1, 3, 1, 2, 3. So notice these two sets are the same set, contrasting with this example where we actually have different sets. Everybody okay? It turns out, I'm not going to do the computation, but you can go through every single element of S3 and put it on the left of n and the right of n, and you will get the same coset. Perhaps you'll get the elements in different order like we did here, but you'll get the same 3 elements, right? For example, if you use 1, 2, 3 times n, you'll just get n back, right? Because 1, 2, 3 is already in this group, and so we'll just permute these elements. And same with 1, 3, 2. But these other ones will give you all the 2 cycles, just like before. Now, in a certain sense, this subgroup is more special. It's better than this one because this one, all that's left in right cosets are the same set, whereas this one, it's a little bit off. Okay, so before I give you the definition, any questions on how we did any of these computations? Y'all see what the difference is? Or your left cosets and right cosets may be different collections of things, right? Okay, so let me give you a definition. Oh, actually, I'll say this form now. We say H and G is a normal subgroup. If its left and right cosets coincide. That is, when you do this little computation, you get the same thing. Put the G on the left, put the G on the right, you get the same collection of elements. Okay, now, before I give, so I'm going to give you a couple of theorems I think that will demonstrate why normal subgroups are important. But first, let me give you something that will be of use to us moving forward. Proposition 541. Let G be a group. H a subgroup of G. And X and Y elements. My conclusion is that and actually we've actually done this before, although I didn't couch it in these terms, so that's why I put this proposition here. You might ask yourself that when do two left cosets, X, H, and Y, when are they the same? So X and H both live in the same coset. They both represent the same coset if and only if X inverse Y is an element of whatever H is. Let me give you a demo of this before I do the proof, right? Notice, here's just a random coset, right? Notice, in fact, we've got two of them. These two elements here represent the same coset, right? I mean, think of coset as a state. You can elect anybody you want as your representative, right? Everybody okay with that? Well, look at X inverse Y. X inverse is of Y, which is 1, 3. Now, what is 1, 2, 3 inverse? Remember how we do the inverse of the cycle. You just run it in reverse. Let's see what this turns out to be. 1 goes to 3, which goes to 2. 2 goes to 1, and 3 goes to itself. And notice 1, 2, how about them apples? That's what this theorem says. X, H, and Y, they live in the same coset if X inverse Y is in them. Right? And we see it works right here by just doing this computation. So let's prove this. Well, let's suppose first. So let me point out that by the way, how do I know that Y is in YH? Remember what YH is? It's Y times H as H runs through all the elements of the group. How do I know that Y is in there? Isn't it supposed to be Y times H?
If H has the identity.
Right. That's the key. H has an identity here. So if you pick the identity, Y times the identity, so Y has to live here. Everybody agree with that? But we're assuming that this is XH. So there exists H and H such that Y is XH. Right? Because since Y lives in here, it has to be, you have to be able to write it on H times H. Now multiply on the left by X inverse, and you get X inverse Y is equal to H. So there's the first statement. If XH equals YH, then X inverse Y is NH. Yay for us. Right? Questions? Now, what about the other direction? But before I get all rabid about going in the other direction, let me ask you, what do you all know about left cosets? There's an important thing. If I walk up to you on the street and I give you two left cosets, XH and YH, I don't necessarily know. One of two things has to happen. Can anybody describe what has to happen with two left cosets? That's right. They either have to be exactly the same or they don't touch at all, right? There's no overlap. That's going to be key here. So let's go the other direction. Now suppose X inverse Y is in H. Let's suppose X inverse Y is in H. Well, this means, let me write out something just kind of, I like to write down things that helps me kind of navigate. X inverse Y is some H and A, right? This means that Y equals XH, which is in XH. So that first little bit tells me that Y lives in the state XH. Agreed? Y has to live here. That's all right, but Y Y also must live in YH just by the observation, Coleman, that you gave us last time. The identities in there, so Y has to live in YH as well. So Y since Y lives in both of these, it's not empty. Therefore, Uchenna, your observation, it's got some overlap, so they have to be the same. So let us keep this in mind here, that X and Y live in the same coset, if and only if X inverse Y actually live in the subgroup H. Okay, let me give you a big theorem about normality. I'm not going to formally prove it so much, but I'm going to talk way through it. It's not too difficult to show, but these are a bunch of different ways that we can describe normal. I've already given you a definition of it. And so here's some equivalent ways to think of it. Let G be a group. And then here. So let N be a subgroup of G. The following conditions are equivalent. So these are basically equivalent ways of saying it's normal. Every left coset of N is a right coset of N. Right coset. 2 Gn equals Ng for all Ng. So these two are, I'll talk you through this, but these are pretty obviously equivalent. And remember, this is what we meant for the group to be normal. 3 G inverse in G. What do I mean by this? I mean a very similar notation to what I mean by Gn. This is just all the crap of the form G inverse little n G as little n runs through all the elements of n. And 4 G inverse little n G is in it. Now let me kind of talk through this a little bit. So all 4 of these conditions, any one of these conditions holds that it's what then n is what we call a normal subgroup. Right? If every left coset is a right coset, well, take a left coset Gn. G has to be in here, and it also has to be in G, so that means Gn equals Ng. What this means is every element of the form Gn1 is a form into G, which means that G inverse into G is N1, which is in N, and these all are equivalent. Okay. Any questions? Now, let me give you an example. I'm going to go out of order of my notes here a little bit. I'm going to skip the next one and come back to it. This will be good practice. I should put this. Okay. Proposition. And actually, in a certain sense, these are the only normal subgroups. And I'll explain that with the next proposition. But phi from G H be a homomorphism. And kernel phi, this is the set of X and G, such that phi of X is the identity of H. Okay, so suppose that we have a homomorphism, G to H, and I am going to define the kernel phi. So this is something that you're going to need to know. This is called kernel. By the way, have you all heard the terminology kernel before? Did anybody hear it in linear algebra? Did you hear null space? Okay, well, that's null space is basically what the kernel is. What was the null space in linear algebra? It was all the vectors that went to 0, right? That's what's essentially going on here. This is what the kernel is. It's all the stuff that actually gives the identity here. Yes?
What is the subscript on E?
I'm sorry. It's an H. I mean for that to be the identity of H over here.
Okay, sorry.
So the kernel is all the crap in G that goes to the identity in H. Now, the first little alarm bell that goes off is like, ooh, what if the kernel is empty? But the kernel is never empty. Can anybody name something that automatically has to be in the kernel if that is a homomorphism? Can you identify anything?
Yeah.
The identity. That's one of the things we prove about homomorphisms, right? Is it takes the identity to the identity. So at least the kernel's got that in it. Maybe some more garbage. But the kernel phi is a normal subgroup. And the notation for normal is sometimes written this way. This means not just subgroup, the little triangle means normal subgroup. Okay. This is kind of interesting because it shows that the kernel is always a normal subgroup. Let's convince ourselves of that. The first thing I need to do is answer the following question. Why is the kernel of phi a subgroup at all? Right? I better convince myself that sucker's a subgroup before I start slapping adjectives on it, right? I mean, forget about being normal. Why is it a subgroup? Well, let's see. What do I need to be a subgroup? I need it to be closed under the operation. So let X and Y be in the kernel of phi. What does this mean? This means phi of X is the identity of H, and so is phi of Y. Notice that phi of Y is phi of X plus phi of Y, which is the identity of H times the identity of H. Therefore, XY is in the kernel of phi. So step one, it's closed, right? If I got two elements in the kernel, they're products in the kernel. Everybody okay with that? What else do we have to do? Well, how about associative? Ooh, I hate associative. Everybody with a soul hates associative, right? You just sit there mucking around with parentheses. Somebody please save me and tell me why I don't really need to worry about associative. Well, that's right, but the problem is there may be more stuff than just the identity in the kernel, right? And that's the problem. But I think you're on the right track. Where does the kernel fit? The kernel is a subset of something. What's it a subset of? It's a subset of G, and G is a group. So I already know that we're associated, our multiplication is associated for everything in G. So that includes the crap down in the kernel, right? So there's already, well, G already has associative operation.
Why can you use that argument for associative, but not for the other ones?
Well, because the problem is I do know that X times Y is still in G. I just don't know what's down in that subset of kernel of phi.
Oh, I see it.
Right. Ooh, how about the identity? This is a property that we learned last time in class, that the identity of G goes to the identity of H. So identity of G is in the kernel of phi. So we got that. And the last piece that we need is inverses. Now, for if X is in kernel phi, then phi of X is the identity of H. Therefore, phi of X inverse is the identity of H inverse, which is the identity of H, because the inverse of the identity is the identity. And this is phi of X inverse. Because I can move that -1 inside. That was one of my properties of homomorphisms that we had last time, that phi of X to the n power is phi of X to the n. So what we've shown so far is the kernel phi is a subgroup. Now we need to show normal. And you know what? I'm going to apply the previous theorem. This is the one for the workaday mathematician like me, right? Because all I have to do is show that G inverse NG is still in N for all G and G. So let's set this up. You need to show that G inverse XG is in kernel. Right? That's what this property says. If I have something in my supposed normal subgroup and I multiply by G inverse NG, then it's still in there. Well, let's check this out. See what happens to this thing. I don't know much, but this is a homomorphism, so I can break this up into 3 bits. Good so far? Now, what happens to this phi of x in the middle? That is correct. We assume that this is in the kernel of phi, so phi kills it. It reduces it to the identity. So another way to write this is phi of G inverse phi of G. Agree?
This might be kind of a dumb question, but why are we using H as the
To emphasize that this is the identity of H as opposed to G, because phi lands X over an H. So this is, okay. So for example, if one of the operations was addition and one of them was multiplication, like with a log or something like that. Now we'll slide this back together. And as to your question now I've got the identity of G, because that thing inside the parentheses is in G. That's the identity of G. And what does any homomorphism take the identity of G to? The identity. So this thing was killed by phi. So we've shown that is normal in G. Okay. Any questions so far? Now, here is the big theorem. This is one of the big. So, okay, this is sort of semi-big, that the kernel of any homomorphism is normal. But this is why we care about normal subgroups right here, because normal subgroups allow you to build new groups from old. So, example. And we've actually done this before, but you probably don't realize it. And I'll give you an illustration of this. If G is a group, then one is a normal subgroup. Normal subgroup. If and only if left cosets of N and G form a group. Under the operation okay. Denoted by G mod N, where it is normal. Okay, now you guys help me out and remember my adage. In math, if it ain't easy, don't do it. So I've got to tell you how to multiply a left coset by another left coset. Now, I claim I'm going to turn this into a group. So when I multiply this left coset by this left coset, I need to get a new left coset. What's the easiest thing you can think of given that formula? XY. That's exactly right. Now, I'm going to show you that this works, but first I'm going to give you an example. And you've actually seen this in action before, although it wasn't couched to you in these terms. Let the integers. I'm going to do something that I can just really write down here. Let N be 2Z. Notice that this is an abelian group, so this is automatically a normal subgroup. The elements of this group are the left cosets. How many left cosets are there? Oh, I've got one. I know what one of them is. One of them is the subgroup 2Z itself. Anybody know what the other left coset is? Okay, right. Add 1 to everything. How do I know I'm done? That's an exhaustive list of left cosets. Right, because every integer, I partition the integers, right? Everything's either even or odd, right? And there's no overlap, so I partition this. Notice that this is the same coset as 6 plus 2z, and this is the same coset as 17 plus 2z, right? Now, what does this operation tell me? It tells me that I add cosets just like the numbers. So what is 2z plus 2z? What happens when you add this even coset to itself? You get 2z back, right? Because think of it this way, take any pair of even numbers and add them up, you get an even number, you can get this coset back. Everybody okay with that? What happens if you have 1 plus 2z? 2z. What do you get? Which coset you get? 1 plus 2z. You bet. What happens if you add 1 plus 2z and 1 plus 2z? By this formula, you should get 2 plus 2z. And think of it. You get everything in this coset by adding all these things up. You all have seen this before. Do you all recognize this? This little group here? It's got 2 elements. this is basically the additive identity here, right? So this is 0 bar, and this is 1 bar. Right? So you can think of 0 bar and 1 bar. Remember, you're thinking of equivalence classes. You're taking any integer, you're dividing by 2. If it's got a non-remainder, it goes into 1 bar, this equivalence class. If it's got 0 remainder, it's even. Right? There's nothing special about 2z. You can replace n by any multiple of anything you want, 5z, 10z, 17z, whatever you like, and you'll get the same thing. You'll get more cosets. Any questions on that? Questions on that? Okay. I'm not going to prove this whole theorem, but I do want to point out. I'll put quotes. I'm not going to do the whole thing, but the important part. Let me point out that notice that showing this is associative is pretty easy because the multiplication in G is associative, right? So because of the fact that G has associative multiplication, this should follow. Can anybody tell me what the identity is? What should the identity? What's the coset I can multiply by xn and it leaves it alone? It's just the identity, right? Because if that's an E, then you leave everything alone, right? So it's the coset generated by the identity, right? What's the inverse of that coset? Anybody want to guess? What do you hope it is? Better be some coset. How about that? What happens when you multiply x inverse n times xn? You get en, which is the identity. Associativity and closure. Closure is actually obvious by the way we set it up. The only question is really, and this requires normality. The only question is, whether this multiplication is well defined. And let me tell you what I mean by that. So suppose these cosets have as many elements as there are elements of n. Agreed? Because remember, all the cosets are the same size. And so if n has got more than one element, these cosets have multiple elements, right? Remember, with my example with the integers, the even integers, how many even integers are there? Infinitely many. So how many choices, how many representatives could you elect? Many of them. You might pick 2, I might pick 4, you might pick -6, whatever it is, right? Now, suppose I elect X to represent this coset and you elect A. Now suppose that I elect Y and you elect B, right? So we've got the same coset, but I picked a different representative, right? I voted for a Democrat, you voted for a Libertarian, whatever, right? But they're from the same state, right? We need to show that's what I mean by multiplication is well defined, because I'm going to go on my merry way and I'm going to say xn times yn is this. And you're going to go on your merry way and you're going to say an times bn is that. We better get the same coset, or this is all screwed up. Ready? If we don't get the same answer, if this is not the same answer, we're in a lot of trouble. So we need to show that that's what it means for these two cosets to be the same. Remember that business that we talked about earlier today, that Bill times N, Fred times N, they're the same coset if Fred inverse Bill is in N, right? Everybody okay with it? So we need to show, let me keep taking this apart, B inverse A inverse XY is in N, correct? Now let me point out that we know which way do I want to do it? We know A inverse X and B inverse Y are in as Xn, En, Yn. Everybody okay with that? So because of the fact that Xn and An are the same, that means that A inverse X is in N and B inverse Y is in N. Everybody okay with that? So let's take this apart. Let's see what I did. Nothing up my sleeve, right? That's almost a cheat. I put a BB inverse there. Everybody agree with that? No harm done. Let me point out that this is in N. And so this is in N. Why is B inverse times this thing in N times B in N? No one? So this thing is an N because of the fact those two cosets are the same, right? But why when I bookend this with B inverse and B, why is that an N? No, because I don't know that I can shuffle that around. But
it's the same element.
No, not necessarily. Well, what do you know about the subgroup N? What do we assume about it? We assume that N is normal. And so that means that B inverse NB is still in N, right? So since that's an N, then B inverse NB is in because it's normal. And this is in N as well, right? Because B inverse Y is in N. So we've got this big orgy of things that are still in N. So that's our multiplication as well. Fine. That is actually central to what we need there. If you don't have normality, then this multiplication, all the stuff about groups, the associativity, the identity, the inverses, closure, that all works here. But if you're not normal, this multiplication is not well defined. That is to say, when I pick my representatives and you pick your representatives, and we do our honest multiplication, we might get different answers. And you need normality to keep that from happening. So that's why this is always important. Notice that G mod N, it turns out that N is always the kernel of homomorphism, as a matter of fact. So that's another tie-in to that. But that's enough for now. We will certainly end it by there. Don't forget the review session tonight. Anybody got any questions?
So this material will be on the exam? Yes.
For the definitions. Obviously, I'm not going to get too deep into this. Oh, any questions out there? Okay, well, hopefully I'll see everybody this evening at 7.